So I think in the fall semester we got just a tiny bit of this. Unfortunately, when I see it in the fall, I remember everything about it, and I'm like, why aren't we saying everything about it? And that was epoxides in the alkene chapter. There's cyclohexene, peroxybenzoic acid. Can we draw the structure of that? We did a lot of recrystallization stuff and extractions of benzoic acid. There is benzoic. So that's a per acid. Remember in Gen Chem nomenclature, per means over, has more oxygen than it needs. And so peroxides, but more importantly, a peroxy acid can make a epoxide, which is this little three-membered ring from an alkene. And then these things are gonna do interesting things. The oxygen can be treated as a substituent using the word epoxy on the compound. Use numbers to specify the position. Excuse me. So notice here the three-membered ring's coming up. This other substituent is going away. Those are the only two substituents on the cyclohexane, sorry. Came from a cyclohexene derivative. So we named this trans 1,2-epoxy 4-methyl cyclohexane. So this is a common name where we start with the alkene and add the name oxide, cyclohexene oxide. We'll stick more with the IUPAC. Ethers seem fine, confusion there. So look, we got a lot going on here. We have the epoxy group, we have an ether group. I just realized I messed up that name in my example problem. You want to name the less complicated part of the ether as the alkoxy, and the longer chain is just the alkane. So here we go. Notice we have a ring. We have the methyl group going down and this group here going down. So this is cis 2,3-epoxy. That tells you where the three-membered ring is. 4-methoxyhexane. Let's start over with this. With the IUPAC 2, and did I get tied up earlier? It's time to retire. 2-methoxypropane. Of course, the common name we just looked at was methyl isopropyl ether. The three-membered ring, oxyurane ring, is the parent. Oxygen is 1 here. So this has an IUPAC name of 1,2-epoxyethane. We run into a substituent earlier this way, so going way back to our alkane, 1, 2, 3, 4, 5, 6. I can't mix the common and the IUPAC, I'll get tied up. So this becomes 3,4-epoxy, 4-ethyl, 2-methyl-hexane. We're not going to bother with these. Straightforward way is to give the number and the epoxy where the three-membered ring is and follow the rest of your IUPAC rules. So spectroscopy is like stereochemistry. It just keeps coming back and coming back. So let's talk about the IR spectroscopy of ethers. The carbon-oxygen stretch is in the fingerprint region. So we never, don't know if it's from an alcohol, but so we ignore that. It says many compounds are going to have this carbon-oxygen stretch. But as was stated in the IR chapter, what is missing is just as important what's there. If the IR spectrum has this stretch, which we may or may not even look at in that fingerprint region, but if it doesn't have carbonyl-carbon, 720 wave numbers, or the OH, that big broad thing at around 3,000, up there on the left side of the spectrum, we most likely have an ether. So like if we had so this was my formula. I know there's oxygen, and I don't see that carbonyl-carbon at 1720, and I don't see that OH up near the left. That's gone, and I see an oxygen. The functional group is most likely an ether. So here's our ether, our molecular ion. Alpha cleavage is between the first carbon and the second on one of the sides of the the oxygen. So we get this carbocation. Those electrons can jump down there. So this is how the carbocation stabilizes itself with this oxonium ion. Main fragmentation is alpha cleavage to form the resonance stabilized oxonium ion. Either alky group can be cleaved this way. Got to stick the word ether in there. Either ether and try and make it into a tongue twister. So if not alpha cleavage, it can also cleave right by the oxygen. So here was alpha cleavage, here's just cleaving and loss of an alky group. We still get this thing called the oxonium ion. This jumps off, and notice there's like some tautomerization going on. There's 2 hydrogens, and it moved up onto oxygen somehow. And then the electrons can jump down, and it becomes delocalized. So the carbon-oxygen bond can be cleaved, produces a carbocation, both called the oxonium ion. So here's an ether, 1, 2, 3, 4. 4 times 12, 48, plus 10, 58, plus 16, should get us to 74. So here's loss of an alky group. 29 from 74 is 45. There's our 45 peak. Let's look at alpha cleavage. This thing's diethyl ether, ninth and symmetric. That'd be loss of a methyl. It gives us our 59. 47 minus 15 should equal 59. Now something interesting says here alpha cleavage. That means cleave right there, we get this thing. Now this thing here can lose an ethylene molecule. So it's almost like this breaks off, but it gives it 1 proton. And here's this thing at 59, or 59, cleaving there gives us this 31, loss of 28 from 59. And that's our base peak. So when I look at this and try and rationalize maybe the base peak, I have to say it must be a kinetic issue, that we're getting a lot of alpha cleavage, and then right after the alpha cleavage, we lose this ethane. So there's still some of this around, but most of it quickly goes to this thing. We see all these. Next up, NMR. So a proton on a carbon, and you've probably already seen this, would be very similar to an alcohol group. Typical chemical shifts for ethers between 3.5 and 4 for proton NMR, and 65 to 90 for carbon 13. So you've seen this before. You're likely to see it again, like on a quiz in midterm, or we don't do midterms, exam 2, and possibly the final, Williamson ether synthesis, an alkoxide, an alky halide, an SN2 substitution, and we could also have the tosylate here instead of an alky halide. How is the alkoxide made? Using sodium or potassium or this sodium hydride. You don't want to miss these on a quiz well, maybe you got something like this going on. Could be sodium, could be lithium, could be sodium hydride, form an alkoxide. So here's cyclohexanol. This is going to form the alkoxide. It's going to slam into that carbon, tosylate leaves. We could also have ethyl bromide. So here's the sodium hydride, makes the alkoxide, slams into here, SN2. So ethoxy cyclohexene. 1, 2, 3, 4, 5, 2 methoxy 3,3-dimethyl pentane. That review is for me. Phenyl ethers. It says here, phenoxide ions are easily produced because the alcohol proton is acidic, so we can make the alkoxide with base, sodium hydroxide. So imagine this thing protonating that hydroxide and having water, then we have this sodium phenolate, 2-nitrophenolate, and that's going to slam into that carbon, SN2 reaction to get to 2-butyloxy nitrobenzene. Phenyl halides or tosylates cannot be used in this synthetic method. It's like when you want to swap those two things around. So in the fall, this came up, and I probably mentioned it. I don't know if we had a lot of quiz questions on it, and typically I'm like, what's going to come up later? And so here it is. Alkoxy mercuration, demercuration. So in the fall we had water here, and we did hydration of a double bond to the corresponding alcohol. Instead of running this in water, we run it in an alcohol. It's going to add to the double bond just like water, in this case with Makarnikov regio selectivity, and so it's a way to form an ether. So here's hex 1-ene, and here's the alcohol this thing's being run in. So we're going to make a methyl ether of some type. Where's the OH OR group. It's going to go on this carbon there. So this carbon has 2 hydrogens. This one has 1. The rich are going to get richer. There you see that carbon now has 3 hydrogens and the alcohol added to this carbon here. And presently I don't know of a similar thing for anti-Makartnikov. And we've seen this one before. Bimolecular condensation of alcohols. So here's ethanol, 2 ethanols in the presence of acid. Get up to 140 degrees, you can get water and diethyl ether. Not used very often in the lab. If it's hard to control temperature, you get alkene formation. And you should think, yeah, alkene, because typically a lot of times if it said alcohol and this in heat, you'd want to write the corresponding alkene. Acid catalyzed dehydration of an alcohol to an alkene. But in industry, they can recycle any ethene that would get formed. So here's N-propyl ether, 75% yield. Here's isopropyl alcohol, and we get that acid catalyzed dehydration of an alcohol to an alkene. Unimolecular dehydration, no ether is formed. Of course, it'd be interesting to come up with reasons why this probably occurs. We don't care. We want to move on. So at the beginning, when we looked at the properties of ethers, we said they're very stable and not affected by base. And I said, well, that's good because we do Grignard's and other organometallic chemistry. And organometallic chemistry, we basically have carbon anions. Carbon anions. However, they're horrible if things get acidic. It says here cleavage of ethers by HBr and HI. And I'd imagine other acids can do it. I imagine that bimolecular condensation reaction is an equilibrium thing because the acid can break it back down and it can go around, but in industry they can just cycle it. So ethers can be cleaved by heating with these acids. Hydroiodic is most reactive. How does it work? Everything we learned in the fall, protonating an OH group makes it a good leaving group. Water's a good leaving group. So here's our ether. It gets protonated by the acid. Now we have a situation where we have like alcohol being a good leaving group. And this is now going to be an SN2 reaction. The alkyl halide can slam into this, and this leaves. So an alcohol is a good leaving group just like water would be. Stable base. The conjugate acid is strong. This must be a stable base. And we form some alkyl halide. So now, of course, you can tell me why HI was the most reactive, and that's because iodide's a better nucleophile than bromine because it's more polarizable. Now, if you have enough of your hydrogen halide around, you could probably do the same thing. Protonate that. Water's a good leaving group. There's our mechanism. This does not occur with aromatic alcohols and phenols, which is aromatic. Bet you can't wait to get to the aromatic chapter. So here's ethyl phenyl ether, or ethoxybenzene. Oxygen gets protonated, bromine hits there, and we have a good leaving group, an alcohol, and form ethyl bromide. But I had to think back when I looked at the slide a while back. SN2 reactions don't occur on sp2 hybrid carbons. What we discussed earlier was SN2 primary and secondary alkyl halides. Doesn't occur on tertiary, and those were all sp3 hybrid carbons. All right, we're gonna end there.